Talk is going to be by Levente Csikor from the National University of Singapore. Previously, last year, Levente presented an earlier version of this work where that was part one of the discrepancy of the Megaflow cache in OVS. In this talk, he will present the next iteration of our Doom. Here you go.
Thank you, Ben, for a nice introduction. So, yeah, as Ben said, my name is Levente Csikor, and I came from National University of Singapore. And this work was done there with my colleagues Min Sook and Dinil from National University of Singapore and TrustWave. So the title of my presentation is The Discrepancy of the Megaflow Cache in OpenVSwitch, which is part 2. So let me have a quick recap about what part 1 is all about. So in part 1, we actually found that there's an algorithmic deficiency in the tuple space search scheme, which is a packet classifier used in the Megaflow cache. We found that actually it's really easy to exploit. So if we know the flow table, so like according to a flow table, which is as simple as allow some but drop others, which is really usual, then actually less than 1 megabits per sec attack traffic can be really bad. So we can achieve a full denial of service in OpenVSwitch using the kernel model. And we also found that it works in public deployments. So all Kubernetes and OpenStack, which were using OpenVSwitch, it was actually vulnerable. And it was vulnerable only against collocated victims. So if we happen to be scheduled to the same hypervisor than our victims, then we can achieve this. And there's no mitigation available at the moment because it's a very low rate attack traffic. I will talk about how it works. There's no specific attack signature. And actually, all the packets that are sending to the system to achieve this goal is completely legitimate. So let's see how it works. So we have a cloud environment here. People are using some services, and we have OpenVSwitches as virtualized packet classifiers on all of them. And people are just using the services in the normal way, so like accessing some services and things like that. And now when the attacker comes into the picture, what it does is to just lease a resource in the cloud. It happened to be scheduled to some of the device, some of the servers, and then it installs its own flow table and then sends packet towards this packet classifier, and everyone who is happened to be scheduled to the same hypervisor switch becomes a degraded packet classification service. So the problem is, so let's see how it works. So usually we have just a flow table. What is a flow table? So flow table is actually an older set of wildcard rules operating on a set of header fields. And also we have a couple of actions, right? We can redefine. And of course the flow rules in the flow table can overlap. It makes it really easy for network administrator to configure how the packets should be routed. Actually in OpenVSwitch, in the kernel space, I'm just using OpenVSwitch and kernel drivers. So I'm not really into the DPDK part. So to fasten the packet classification itself, this is something that everyone should know, I guess, about OpenVSwitch, that only the first packet is actually sent through the slow pass in the flow table to find how to route that specific packet. And whenever we have a hit or any result, then we can actually cache it. And then it will be represented in the fast pass. And then all the subsequent packets which are coming into the switch will be handled really quickly. Even in the OVS kernel model, it's really quick. It can be 10G, for instance. And this is what actually I'm going to talk about. So there's the tuple space search scheme, the packet classifier, which is implemented in the kernel model. So let's see. Okay, so let's see how tuple space search actually works. So we have entries matching on the same headers are collected into hashes where the mask packet headers can be found fast. So usually when a packet comes in, we have a flow table like this, and we have the hashes, the masks, and the corresponding hashes here. So whenever a packet comes in, we just apply one of the masks and then see whether we can have a hit. If we don't have, we just go through, and it can be a really long-lasting linear search problem. So this is what we can actually exploit here. So the key finding is that if we are able to generate as many masks as possible in the tuple space, then actually the more masks we have, the slower the packet classification itself can be at the end. So for each allow rule, so if you know the flow table, for each allow rule, there's a corresponding packet sequence to achieve this end. So if you give me a flow table, I can tell you what are the packets that need to be sent to the packet classifier itself to achieve the highest number of masks in the tuple space. So the strategy was that if we know the flow table, which is like this one, LO destination port 80, it's a typical flow rule actually for all the web services nowadays in the cloud. So then we generate one specific packet for the LO rule, and then we just add the packet with each of the relevant bits inserted one at a time. So with one packet, I can generate one MFC, Megaflow cache mask. So let's see how it works in an animated way. So actually, the animation itself took more time for me to make than the attack itself. So we are just sending one packet at a time, and we are just generating all these masks in the system. So let's see, it's so beautiful. I mean, I spent like 2 hours on the flight to make this. So this is the aim. This is what we want to achieve. And now let's see the numbers. So for a 16-bit of destination port filter, so if you have 16 bits, then we can generate 16 masks. If we have a filter, for instance, in a source IP, which is 32 bits, then we can generate 32 masks with 32 packets. And that's only just one LO rule on one header field. So the problem is that we can imagine that if we have multiple LO rules, then the whole problem can be really bad. So it's an exponential growth because of the cross-product problem. So if we have a simple flow rule or flow table, which is like allowing port 80 and allow some communication from other VMs from like 10.0.0.1, which is again a really typical ACL people usually implement, then it can be 500 or 512 masks. And now I'm going to show how bad it can be. So we're using a open vSwitch kernel model, as I mentioned, and although we have a Mellanox card, which is capable to offload the caching mechanism to the hardware, which means that it should be really fast at some point. But either way, we found that actually, if you are generating somewhere around 100 Megaflow masks, which is really simple according to the information that I told you just before, then you can see that with 100 masks, we can achieve like below 10% of the attainable throughput. And it also applies for, even if we have a full hardware offload, that's the dotted line here. So if we generate, this part actually is this case. So we have 8,000 masks. So we have a filter on the source IP, we have a filter on the source port, and we have a filter on the destination port. That's all. With 8,000 packets, I can generate 8,000 entries in the mask. And even if you're using a full hardware offload, I can actually reduce the performance from 30 gigabits per sec to just 1 gigabits per sec. So it's a really a bad thing. So let's finally talk about why am I here this year. So in this talk, I'm not going to present any new deficiency or any new algorithmical problem of the whole packet classification itself. I'm not going to implement another packet classifier, and I'm not going to improve the packet classifier, which is here. So why I'm here is actually to talk about that from an attacker's point of view. Can the case be even worse? So can the attack be more generic because if you are an attacker in the previous case, I needed to know what is the flow table, and according to the flow table, I could generate the packets. But if I don't know the flow table, then it's a more generic kind of attack. Is it passable? This is the question that I'm investigating here. Is it passable? And the other thing is that in this case, I'm not going to be co-located with any of the victims I'm trying to attack. In the previous case, it was assumed that I happen to be scheduled to the same guys, and then I can degrade the service to the guys who are actually scheduled to the same hypervisor. And of course, I'm going to talk about what countermeasures can we have, because last year we didn't have any. We were just proposing the problem itself, and we had some talks even with Ben and the other guys at VMware to figure out something. Okay, so now the case is that people are again using services, but now the attacker is just not randomly being scheduled to some of the hypervisor. It figures out that, okay, I want to attack the services like the email services. So I'm just sending the packets towards that hypervisor, and I don't have any assumptions. So I just pick my victim, send the packets there, and I try to ruin the packet classification on that specific server. This is what we are trying to achieve here in this general use case. Okay, so the challenge is that, again, we want to blow up the Megaflow cache in the same way as we did before, but now we don't know the flow table. Is it possible? how much effort do we need, and how success we can be as an attacker, and what are the countermeasures. These are the things that we are investigating. So how to generate the packets, that's the biggest question in the beginning. Since we are not aware of the flow table, it's difficult. We don't know the masks, we don't know the hashes, we don't know nothing, actually. So one might think that let's generate all the possible packets for a given header field and that we're good, right? But the problem is that it really requires too much effort, and actually even if just 2 flow rules are there, we need to send like 3 petabytes petabits per second to achieve the goal, which is really easy to detect, right? So even if just the port scanner, it becomes a volumetric attack at the time. So it's really easy to handle. So I'm coming from the academia, so what people usually think in the beginning that how about random things? So random, any algorithm which has some random parts happen to be successful in many algorithms in the past. So we just simply use that case. Okay, how about generating random packets? Can we be good with random packets? And the thing is that we figured out that it's not even that good, but it's not really bad. So what are the chances that if I generate a packet, I will generate a Megaflow cache mask at the same time? So I have, again, a very nice animation here. So the chance actually that we are generating a packet, it will be part of that specific mask, which is here. It really depends on how many wildcarded bits we have in those masks. So we can see that this number, actually this port number, and the associated hash, according to the mask, which is here, we have 15 wildcarded bits. So it means that this is the probability of a random packet that it will generate that specific mask. So it can be seen that it's 50%, although if we want to generate a packet that will spawn another Megaflow cache entry, the chances can be much worse. So let's see how good can we be. So we have a measured and expected numbers according to these findings, and we found that if we actually generate just 1,000 packets, random 1,000 packets, we cannot achieve 1,000 Megaflow cache entries as in the previous case, but we could achieve actually around 100. And we saw from the previous plot that achieving 100 entries actually in the Megaflow cache can be really bad. So we can achieve like 10% of the performance drop. Yeah, so the same attack rate, which we had before for a full-blown denial of service attack, if you're just randomly doing that without knowing the flow table, we can achieve 90% performance drop, which from an attacker's point of view can be really appealing, I would say. So it meant in our system that we have 10 gigabits per sec, and then we can reduce the performance to 1 gigabit per sec. So what are the countermeasures? So the detection itself is still really hard. We are still sending legitimate traffic. We have no attack signature. Now we have completely no attack signature. The packets are full random. So it's really difficult to detect it, and it's still a low attack rate. So we're just sending a couple of thousands of packets per second. It's not a big thing. So we, as a really preliminary countermeasure, we developed Megaflow Cache Guard. It's a simple application which tries to monitor the Megaflow cache. And whenever it sees that there's a lot of entries according to this attack, it tries to wipe those entries out and try to see whether it can be a countermeasure or not. So how it means that the attack traffic actually we're going to send up to the slow pass again. So according to how the caching system in OVS works. So the benign traffic will be still handled in the fast pass in the cache, but since we are wiping out all the entries corresponding to the attack packets will be sent upwards. So this is how we try to achieve our goal. So usually this is how it looks like. So we have the benign useful traffic, and of course we also have the attack traffic, which is a low latency attack traffic. They are crossing through the kernel space, and then we are just figuring out. We see how big cache growth actually we are having at the moment, and then we just remove all the corresponding entries from the cache. It's not a straightforward task, but we have OVS dpctl command to control the cache itself, so we can remove some entries, and then it would result in that all the attack traffics are now going up to the slow pass, but the useful traffic will still be in the fast pass. And we found that actually if we clean the Megaflow cache in this way, then it's successful in terms of as a countermeasure. So the normal throughput will be reached again. Although we found a neither documented nor expected behavior, because usually one would think that if I send again a packet up to the slow pass, then it will again cache that entry and put it back, right? So I would need like a continuous monitoring mechanism which will always delete the entries. Although we found that whenever we removed an entry with the dpctl command, then it won't be cached anymore. It was an interesting thing, I guess. I did even ask Ben, and he said that there's no documentation actually available, so it's not, no one really wants to do that. So people are not really interested in that. So it means that whenever I delete an entry corresponding to attack traffic, I will have an increased overhead for the CPU, because now all the attack traffic will be handled by the slow pass, which is really bounded by the CPU and all the resources that we have in our system. And what we can see here is that if the random packets are coming in as like 1 kilo packet per sec rate, and now I'm sending those 1 kilo packets up to the slow pass all the time, then actually I have a 15% of overhead in the CPU. I was just using top, the regular command in Linux top, to see how it changes. And if we are sending much more traffic, so this traffic, 1 kilo packets per sec traffic, as we've seen before, it's enough for a 90% of performance drop in this random case. So we can actually avoid this by some extra 15% of overhead. Although if the attacker is really bad and it tries to make as many Megaflow cache entries as possible, we can still handle this attack by wiping out the entries from the Megaflow cache, but then it makes like 80% of overhead, and it can be even higher if the rate is again higher. So this is a live recorded demo we had. So we have the throughput here. I try to show here as well. So and we are going to launch the attack. So we have a monitor for the throughput on the bottom, and we have a monitor here, the number of caches in the system. So this is how they increase. So what we can see here is that I'm sending the 100 packets. Then the Megaflow cache entry, the Megaflow cache numbers are increasing here, and then I can see how the performance drops here. Now I didn't want it to have a full-blown denial of service attack, just a simple one. So I'm generating 100 or something entries, and then we're using a typical offloading technique, then I can achieve a degradation of service here. So now, yeah, I'm already after the point that I cleaned the Megaflow cache. So that was the one from terminal up above. So then I clean the Megaflow cache, and then the attack can be, the useful performance can be go up again to its normal one. Yeah, so that was just a live demo. So the problem is actually we need a more sophisticated algorithm than that. So now I'm currently just wiping out all the drop rules, for instance, from the cache. But we need to maintain a good balance between the CPU overhead and the throughput that we can achieve in the fast pass. So we were also thinking about whether to have a dynamically set timeout in the Megaflow cache. So normally, as far as I know, whenever there's an entry in the cache, it will be warm for 10 seconds. So when there's no corresponding packets, it will be wiped out automatically. But maybe we should not have a uniform 10 seconds of timeout. Maybe we should have a dynamically set timeout. So whenever we have a hit, for instance, in the beginning, all the entries have a timeout of 1 second. And whenever we have a hit, then we increase it to 2 seconds. And if we have more hits, then we are increasing it up to 10 seconds. So it can be a dynamically set, and that can actually be helpful. On the other hand, one can think about prioritization. So how about prioritizing the masks which are for the useful traffic and not for the bad traffic? So these are just some things that we are considering at the moment, but we only implemented the simple one which I showed you. So as a conclusion, we have this tuple space algorithm which has an algorithmic deficiency, and it's implemented in the kernel space for packet classification. And it can be, the algorithmic deficiency itself can be exploited by an attacker quite easily. So we demonstrated this tuple space explosion attack, which can launch against the infrastructure via co-location. That was a part 1 talk I had last year. And then we can achieve a full-blown denial of service. And now we are capable to launch the attack against any arbitrary service, not a full-blown denial of service, but we can degrade the service significantly. And now we have at least a really simple but still working countermeasure, which is the Megaflow cache guard, which keeps the fast paths clean for the benign traffic. Thank you. That would be my presentation. And we have a QR code here, which actually points to some website where all the fresh results about this research is maintained. Thank you.
Let's thank our speaker. So we have some time for questions. Does anybody want to ask one?
Hey, Levente, very good presentation. Thanks very much. I wondered, have you considered a particular technique that I kind of refer to as subtable folding? So you mentioned that you have this explosion of different tables where each one has a unique mask, whereas you could consider an approach where until a packet or until a particular table has, let's say, more than 10 flows or 10 packets hitting that you essentially always compute all the data for that. And in that way, you don't have this explosion anymore because you kind of put all of them in the worst case bucket. From an algorithmic point of view, I think this bounds the maximum number of tables you can have at the expense of doing more compute for each packet that hits that table. I was wondering, had you considered something like this before? And if you had, what your thoughts were?
Thank you for your question. Actually, everything which you said makes sense. We really didn't want to touch how the algorithm itself works. So it's, I guess, maybe in the DPDK version, you're wearing a DPDK t-shirt, so that's the reason why I'm asking this. So I guess in the DPDK version, all this, we don't really have this problem at all. And the other question, I mean, I guess your main question is actually directed to the developers themselves. So it really depends on how they are going to change this. So we just wanted to show the problem itself.
Thank you. So I believe your heuristic is trying to detect an attacker, but then why are you trying to continue giving service to it? Like, why not just completely cut him off? Are you afraid of false positives? Is that the aim?
If I get the question properly, so you ask, why don't we just try to send as many packets as possible to have a full-blown denial service all the time? That's the next step. How you will do? What will you do whenever you detect itself? So it's the problem is that it's really difficult to detect. So so usually when you have the service degradation, by a simple monitoring algorithm in the cloud will not tell you that there is a problem. Some of your users or your tenants will be asking you that, hey, I'm experiencing a really bad performance. What is happening? And then as an operator, you can check what's happening, and then you can also at the end carry out the necessary steps. But until that, it can be, I guess, hours or even days to find this, and then you can block it, of course.
Have you studied other kind of denial of service with a few packets for upcall or revalidator or other table? Have you explored other possible vulnerabilities? And if not, is it in your plans?
We have not really explored any other possibilities. So the reason why I'm actually here is to get some inputs from the guys who are close to the working source codes and working solutions. So thanks about that, and we will check how they can be applied.
Do we have any questions online? I don't think we've taken any yet. Nope. Did I see a question back there?
So one more thing I'd like to point out is at the point where the number of tuples is increasing, the flow add, if you're trying to do any kind of offload to kernel, you're going to experience a head of line blocking over there because the number of tables you're matching. Do you see that as a problem? Did you consider that there might be a head of line blocking for valid flows that are going to have to match a fair number of tuples when the number of tuples in a tuple space goes up significantly, like in this attack that you're talking about.
So the thing is that actually what you can see here can be also the result of a normal operation. So in vSwitch, we also have another, so the caching architecture itself is multi-layered. So we have a microflow cache, which is below the megaflow cache, which is an exact match cache, and it tries to somehow alleviate this issue. So if we have multiple caches, then we can cope with many difficult packets and routing systems. So the thing is that what you are actually mentioning is that is there any upper bound for a software packet classifier? And there will always be. So with microflow caches and megaflow caches, we can easily handle thousands or hundreds of thousands of flows quite efficiently. And above that, you need some other solutions. You need other offloading techniques or better algorithms.
All right, we're out of time for questions, but I bet Levente would love to talk about this in more detail during the breaks or the lunches. Let's thank our speaker one more time.